so welcome to this next video in linear programming. This video is on canonical forms. So at the end of the previous video, we were talking about basic solutions and how if the system AX equals B has a solution, then for a given basis, it has a unique basic solution. And the purpose of putting a linear programming canonical form is that it's going to make it particularly easy to find what the basic solution is for a given basis, and in addition, it'll make it particularly easy to find even better solutions to our linear program. So we'll be able to immediately find a basic solution, and then we'll find even better solutions thanks to the convenient format of the canonical form of the linear program. And by better, I mean we're going to be able to make this objective function C transpose X plus Z naught even greater by changing X. Okay, so this is where we start off with our linear program standard equality format and our basis. But you'll notice that we have this constant Z naught that I usually don't include. It doesn't actually make a difference whether we have this constant added on to the objective function or not, because the solutions X that maximize C transpose X are also going to be the same solutions that maximize C transpose X plus Z naught, since we're just shifting by a constant amount. So then you might ask, why are we adding this constant on at all? And the answer to that is because we're going to do some manipulations of this linear program format in this video to put it in canonical form for a given basis. And these manipulations might include adding on a constant to this objective function. And so it's possible that we'll have a constant, and so we might as well incorporate having a constant right from the get-go. So canonical form is a special format within standard equality format. So it will still be in standard equality format, but it will have even more properties now, which is that it will be in so-called canonical form. And we're going to show that as long as this system AX equals B has a solution, we can put our system into canonical form for a given basis. So if you choose different bases, you're going to get different canonical forms for your linear program. Now let's assume that we do have a solution to AX equals B, because if this system was inconsistent or infeasible, then the entire linear program would be infeasible, since we can't even satisfy this system of constraints, never mind also the non-negativity constraints. We haven't even solved this. We can't, so we wouldn't even be concerned with the overall linear program. So we're only going to be concerned with when this system AX equals B does have solutions. And so moreover, what we're going to do is we're going to assume that this matrix A is full row rank. And we can do that because if this we can just do row reductions of our matrix A, and we can then eliminate any redundant rows, and correspondingly eliminate any redundant constraints of the system AX equals B. And so you eliminate all the redundant constraints until you end up with a matrix that will then be full row rank. That is to say, all the rows of this matrix A will be linearly independent. And so therefore, as according to the previous video, when you take a basis of the matrix A and take the submatrix that corresponds to that basis, it'll be a square matrix that will be invertible, as we were discussing in the previous video. But okay, so that's where we're starting in this video, and we're going to show how to put this in canonical form. But first, it would be nice to know what it means to be in canonical form. So here's a definition. So an LP, a linear program, is in canonical form for a basis B. So underline this, is in canonical form for a basis B if, and there's going to be two conditions. Here's condition 1 and condition 2. If both of them hold, then this will apply. But first, we need to know what the basis B is. That is to say, you have to give me the linear program, and you have to give me a basis B. And once you give me both of those things, I can put this linear program in canonical form for this basis. Okay, and so what are the two conditions? Condition number one is that we need the submatrix A sub B to be the identity matrix. And how many, what index should I put here? Well, I'll just tell you. it's M, the M by M identity matrix. And we know that it's got to be M because that's how many rows there are of the matrix A. And we are now assuming, without loss of generality, that the matrix A's full row rank. And so the submatrix will have as many rows as the original matrix. And so that's why, and it's square, so M by M. Okay, so that's the first condition. We need the submatrix indexed by the basis B to be the identity matrix. And the second condition is we need the subvector of C that's indexed by B to be the zero vector. Or in other words, we need C sub j to be 0 for every index j in the basis. Okay, and so if we satisfy these two things, our linear program is in canonical form for this given basis. Let me just box this off. Okay, so it's actually pretty easy to show that we can always have these two conditions hold. And that's what we're going to do with the remainder of this video. But first, just note that when we start off, if you give me my linear program and the basis, there's no reason that for instance, that A sub B has to be the identity matrix. It certainly does not need to be that. What we're going to do is we're going to do some manipulations of the linear program so that we can, so that we do achieve this and these two things. But at the start, there's no reason that these conditions would need to hold. But here's how we do make them hold. So let's start with the first condition. So we start with our system AX equals B, and here's what we're going to do. Let's just multiply the left and right hand sides by AB inverse. So AB inverse times A times X equals AB inverse times B. And we move that up a bit so we can still see. Okay, so we just multiply left and right hand side by AB inverse. And remember that AB inverse necessarily is invertible because it's the submatrix indexed by the columns B, and we're assuming that A is full row rank. So all the rows are linearly independent, and so then we also have rank many columns in our submatrix A sub B as well. So it's square, and those columns form a basis, so they're linearly independent, and so that must mean that the matrix is invertible. And so that's why AB has an inverse, which is what we call AB inverse. And so that's why this matrix exists necessarily in the first place. But why do we do this? Why do we multiply left and right hand sides? Well, let's call this new matrix AB inverse times A. Let's call this A bar. And let's call this vector on the right hand side, AB inverse times B is a vector. Let's call that B bar. And so we have A bar times X equals B bar. And it's equivalent to the original system of equations, AX equals B. And that's just because we multiply by an invertible matrix. So any solution X that solves this new system solves the original system and vice versa. And we can show that by multiplying by AB or AB inverse, depending on which direction we're going in. But that's why these are equivalent systems of equations. And so I can replace this system of equations by this system. And now what's happened is that our new matrix A, which is what we're calling A bar sub B, that is the M by M identity matrix. It's true. And that's simply because, where do we start? How do we get this matrix A bar? We got it by multiplying A by AB inverse. And what is AB inverse? It's the inverse of a submatrix of A. And so if you look at the indices of A corresponding to the basis B, then that part of the matrix A is going to cancel out with multiplication by AB inverse, because the this is the inverse of what's contained in here. And so these are going to cancel out just by how matrix multiplication works. And of course, there's other columns inside the matrix A as well, and we don't know how AB inverse is going to interact with those columns. It's just going to be some random multiplication going on there. We can't say how it's going to work out, but we do know. But none of that matters. The part that does matter is for the indices, for the columns of A corresponding to the indices of B. Those do get inverted thanks to the fact that we're multiplying by AB inverse by definition. And so if I look at this new matrix that results A bar, and I look at those columns corresponding to the indices of B, I will get the identity, because the columns undid each other by multiplying by the inverse. And just working out a simple example would immediately show you that that's true always. Okay, and so we've achieved this first condition. Our new system of equations is A bar x equals B bar, and for this A, matrix A, which we're calling A bar, the submatrix indexed by B is the identity matrix. Okay, so that's how you show the first condition. And now we're going to show the second condition, which is a little bit more involved, but nothing crazy. But let's just work over here. So we have, we're going to start with the system of equations, AX equals B again, the original system, AX equals B. And we're going to take a linear combination of the rows of the matrix A. And so that correspondingly, and we'll call that linear combination y's. So we'll call this y transpose times A times x. And then we do the left-hand side, do to the right-hand side. So y transpose times B on the right-hand side. So we took a linear combination of the left and right-hand sides and of the rows. And we know from linear algebra, like, you know, if you want to take a linear combination of the columns, it's the matrix times a vector in that order, matrix vector. But if you want to take a linear combination of the rows, it's transpose of the vector times the matrix. So vector transpose matrix in that order. And that's taking a linear combination of the rows of A. So in other words, we're taking a linear combination of the constraints. Now, we don't know what the linear combination is yet. I haven't told you what y is. We're going to determine that later on, so that we're going to choose it in such a way that will satisfy the second condition, although it's not clear where we're going just yet, but you'll see. And how many dimensions should this vector y have? It should be m-dimensional. Y should be consisting of components y1, y2, up to ym. That's because we're taking a linear combination of the rows. How many rows of A are there? There's m rows. So there should be m components for this vector y here. Okay, and so we have this equation here. And now we're just going to subtract. So we have y transpose B minus y transpose AX equals the number 0. And what we're going to do now is we're going to change our objective function. This is going to call back to why we have this strange constant z0 here. But here's how we're going to change the objective function. We're not really going to change it formally at all, but C transpose x plus z0. Now we're going to add 0 to our objective function. But what's another expression for 0 is this on the left-hand side. So we're adding 0 to our objective function in a funny way. So we're not actually changing the objective function, but we are changing the format. So let's add 0. So plus y transpose B minus y transpose AX. And now we can see that there's a common factor x in here. So I can rewrite this as C transpose minus y transpose A times the vector x, and plus this constant, plus z0 plus y transpose B. So again, you can see that this is a row vector times x, so dot product of two vectors plus a constant. Y transpose B is a constant. So constant plus constant is constant. And so now you can see this addition of this new constant is why we had the old constant there, to just account for the fact that we might be incorporating a new constant, but we just always have a placeholder symbol for a constant. But okay, so similar to before, let's call this new vector here, let's call this C bar transpose. And it is transpose. Remember, this vectors by convention are column vectors, so this transpose means it's a row vector. And this is a row vector here. C transpose is a row vector, and Y transpose A, this is a linear combination of the rows of A. And so this is a row vector. So row vector minus row vector is a row vector. So we write it as a row vector, so it's a transpose of a column vector. So this is C bar transpose X plus, let's call this Z1. So this is C bar here. This is Z1 for a new constant. And so this is our new objective function, C bar transpose X plus Z1. And of course, remember, this is actually the same objective function as before. All we did was add, well, we did nothing. We added 0, but we added 0 in a funny way to change the format of the linear program. And so we have a new C vector here. And so now we want C to be such that C sub B equals the 0 vector. And remember C, so what is C bar? C bar well, if C bar is this, then if C bar transpose is this, then C, sorry, this should be a transpose here. Anyway, if C bar transpose is this, then C bar is the transpose of this. So C bar equals C minus A transpose Y. So anyways, I wrote this out just because to point out that C bar depends on Y. And so what we want is we want C bar sub B to equal the 0 vector. So this is what we want. But C bar sub B equals C sub B minus A transpose sub B times Y. And it's not Y sub B, it's just the full vector Y here. If you do the multiplication, you'll see that this is the correct indexing of everything. But yeah, so this is the submatrix of A transpose indexed by B. Right, anyways, so we want this to be 0. How do we get that? Well, we're basically, what we have is, we can move this to the other side. We have C sub B equals AB transpose times Y. And so now we just want to solve for Y. And if we solve for Y appropriately, then we'll get that C bar sub B is the 0 vector, which is what we want to satisfy this definition. So what should Y be then? Y should be equal to, it'd be nice if we could multiply by the inverse of this matrix, so that we would have Y equals AB transpose inverse times C sub B. And so the question is, can we do that? Is that true? Is it true that this matrix AB transpose has an inverse? And the answer is yes, it does. And so this is another fact from linear algebra. It's the fact that transposing and inverting matrices are commutative operations. That is to say, assuming a matrix does have an inverse, then if I take its inverse and then I take its transpose, that's the same thing as if I would have first taken the transpose and then taken the inverse. Those are the same matrix. And we already know that the original matrix AB does have an inverse. That's what we've been saying over and over. And so, of course, every matrix has a transpose. And so then the inverse transpose matrix exists. And so then also we could reverse the order. And so that must mean that AB transpose has an inverse, which is also that same matrix, the AB inverse transpose. And so so we call that A sub B. And then typically we put, I'm running off the page here. sorry about that. AB inverse transpose C sub B. I don't. You might not have been able to see this before, but hopefully it was clear that I was just multiplying by the inverse on this side. So I was just talking about AB transpose inverse times this vector C sub B. Yeah, I always get carried away talking and I forget to look at the screen to make sure everything's on screen. I really got to get better about that. But anyways, this is what we get. We get y is AB inverse transpose C sub B. And so if you choose your y, which is what we started with up here, if this is what you take your y to be, then you do get that C bar sub B will be 0. And so taking your new objective function to be C bar transpose X plus Z1, which is the same thing as the original C transpose X plus Z naught, but it's reformatted because we added 0 in a funny way, your new vector C, which we're calling C bar, will have this property that the subvector indexed by B is 0. And so we've satisfied this second condition. So okay, if we start with this linear program here, then we can put it in canonical form by saying max C transpose minus Y transpose A times X plus Z naught plus Y transpose B. That's our objective function, and the constraints are AB inverse AX equals AB inverse B, and still non-negativity, x greater than or equal to 0. And this is equivalent to the original linear program. This is the same objective function, and this is the same system, an equivalent system of constraints here. And we should say assuming y equals, so you choose y to be AB inverse transpose times C sub B. That's what you take the vector y to be. And then this is equivalent to this. And that shows that as long as AX equals B was a feasible system, which we're assuming because we're trying to solve feasible linear programs, of course. Assuming this had a feasible solution, then it has basic solutions for every given basis, and for any given basis of the matrix A, we can put it in canonical form for that basis, and this is how you do it. And so we're going to see in subsequent videos how this canonical form is helpful for us to find our basic solution and for this basis B, and subsequently find even better solutions for X here. But those will be for the next videos. This video is just showing that we can always put a linear program where this is a feasible system and A is full row rank, and without loss of generality we can assume those things. Then we can always put our if we're given a basis B, we can put our linear program in canonical form, and we do it by this process here that we've just gone through. And one final thing, just it might have seemed, maybe at some points that it was maybe dubious whether the dimensions worked out or not with all this multiplication, but in fact they do all the time. For instance, down here at the very bottom, we chose y to be AB inverse transpose C sub B. At the top, I had said we wanted y to be m components here, and so it's to work out so that we're taking a linear combination of the m rows of this matrix A, and so it's not really obvious, at least at a glance, whether this is m dimensional or not, but it is. I mean, every matrix multiplication is a well-defined thing, and this all works. Remember that this is a basis B, consists of the same number of components as the number of rows of the matrix, because we've assumed that our matrix A is full row rank. And so actually the size of B, that is to say the number of indices, is M. That's because it's a full row rank matrix A. And so this really is an M-dimensional vector Y that we've picked out, and so forth. For everything, that was probably the hardest to see, but for all these multiplications all throughout, dimensions always work, and this is the process that you go through. So anyways, that's just something I wanted to point out before I finish this. But that's the end of this video. In the next videos, we'll go through some examples and then see how this is all useful for creating the simplex algorithm. So thanks for watching.